helpless kids.
And for our project, we are going to be expanding marshmallows in a microwave, measuring their heights at 5-second intervals, and finding the rate at which the volume is increasing at a point that we did not measure. Our problem is to find out how fast the volume of a marshmallow is increasing when the height is 11.9 centimeters and the radius is 5.95 centimeters. For our experiment, we were able to find 4 marshmallows of similar size, each one with about a height of 4.5 centimeters and a radius that's exactly half that, making results much more consistent.
So now it's time to actually heat the marshmallow up. To contain the marshmallow, we used a measuring cup coated with PAM cooking spray so the marshmallow is easy to remove. It doesn't work that well, and by the end, melted marshmallow is going to be completely coating the measuring cup. The marshmallow begins to shrink as soon as the microwave is turned off, but it was pretty obvious that it reached a height of at least 7.5 centimeters.
We did the same process 3 more times and collected the height of the marshmallows every time. Halfway through, we had to upgrade our index card because 12 centimeters wasn't long enough, but we still got the same results. Okay, now that we have our results shown here, we can enter them into a graph on Desmos, which ends up looking like this. This is an obvious logistic regression, so finding the rate of change at one point where there is no constant rate of change is too advanced for us currently. So, to make it easier for us non-advanced calculus students, we can compress the curve into a straight line so the height's rate of change will be constant, making our calculations possible. If you look behind the best fit regression line there and see the straight lines connecting the points, those are the ones that we're using for the height.
Okay, now this is the mathy part. It's really confusing and took us forever to figure out, so we're going to do our best to explain it. First step is to determine which variables we are going to be using. In order to find the volume of a cylinder, we use pi r squared h. So the first 3 variables of our problem are volume, height, and radius. And since we are determining the speed at which the volume increases at a certain point, time is also a necessary variable. Therefore, we have 4 variables in total: time, volume, height, and radius.
Next, we need to find the rate at which the height is changing between 20 and 25 seconds because our height, 11.9 centimeters, is located between those points. Keep in mind that we alter this value to be a constant rate over 5 seconds as opposed to an inconsistent value due to the properties of logistic regression. To find the height's rate of change, we simply take the height that the marshmallow grew over those 5 seconds, 1 centimeter, and divide it by 5. This gives us 2/10, which is how much centimeters the marshmallow's height increased each second. And if we divide that in half, we get 0.1, which is how much the radius grew each second as well. Additionally, since we know the height increases at 2/10 per second, that makes the time exactly 22 seconds when the height equals 11.9. At first, we didn't realize this and chose the number 11.9 at random, but we really should have made the problem, how fast is the marshmallow's volume expanding at 22 seconds, instead of giving the height and radius.
Now we have to differentiate the volume of a cylinder. It's a little tricky since there's more than one variable to differentiate, those being height and radius. But only one rule is necessary, that's the chain rule. We are aware that we could substitute r for a ratio compared to h, which would be equal to 1/2 h, but we decided to do it this way since it shows all the variables. So, when we do the chain rule for the same equation twice, but with respect to different variables, we simply add them together and obtain the equation needed to solve our problem.
But wait, now we have a problem. We have no idea what dH over dt or dr over dt could be. Just kidding, we solved them in our first step when we found the constant rate of change of the height and radius. dH over dt is the relationship of height compared to time, also known as the rate of change. The same goes with radius.
Now all that's left to do is plug in the numbers and hope we get an answer that seems correct. And voila! The marshmallow's volume is increasing at a rate of 66.7 centimeters cubed per second at 22 seconds.
That concludes our exhilarating calculus tutorial. We hope you enjoyed.
Sus.